Hello, everyone. Welcome to MACSMIN 2025. It's a great pleasure to introduce Professor Jason Hattrick-Simpers from the University of Toronto, who will talk about understanding and mitigating bias in autonomous materials characterization and discovery. Over to you, Jason, please.
Okay, thank you, Vitaly, and thank you all for joining this afternoon. Okay, especially on a Friday after lunch. My talk's gonna be maybe a little bit on the different side. To be clear, starting off, I'm an experimentalist. My background is in combinatorial materials science. I build experimental platforms that make and synthesize materials rapidly. And over the past 15 years, we've sort of generally transitioned into AI aficionados and then informed skeptics of AI. And so let's talk a little bit. First of all, let's take a little pre-quiz. If you have an opportunity, please go ahead and pop over into this QR code and let's see how strong our personal biases are in terms of how we view material science and AI working together to discover new materials or to make new discoveries in general. I understand many of you may be mathematicians. So I'm just going to let y'all sort of scoop through those for a minute.
Yeah, great to start with a quiz. I have
Perfect.
completed.
Okay, let's move on. So, and I'll be answering these questions as we roll. It's going to be fun. So first and foremost, I'm a part of the Acceleration Consortium here at the University of Toronto. And what it is it's a $500 million investment by the Canadian government, the provincial government, and industry in the development of a user facility for self-driving labs here in Canada. And so it's important, like what's a self-driving lab? We're in the AI space. We know what a self-driving car is. And what we can think about is in traditional materials discovery, we start with very limited training data. We maybe, if we're sort of elegant, we'll take that through exhaustive graduate student transcription and then turn that into some sort of data to build an AI guided model. The graduate student will then go and make the sample, walk it over to a tool to characterize it, get information out of it, repeat the cycle many times until finally they discover something that's new or interesting. And so this is time consuming, it's costly for industry and for academic labs. The idea of a self-driving lab is a person like me builds experimental platforms that are automated, that can make things in an automated fashion, that can characterize them in an automated fashion. And we've become increasingly adept at talking to our computer scientist friends and our mathematician friends to help them understand our problems to make good AIs. Why am I the person that's moving the samples between spot to spot? Why am I the person that's deciding on what experiment to run again? Could we let the AI make the decision and directly talk to the instrument? Say, make that sample, make 50-50 iron manganese, test it, do the data analysis, re-up its model, and continue this cycle until it makes something new and interesting. So the Acceleration Consortium, briefly, we're a user facility in the making. At the University of Toronto, we have 6 self-driving labs. Myself and Dave Sinton from mechanical engineering co-direct the self-driving lab 1, which is for inorganic materials. Each one of these labs is staffed by up to 5 staff scientists, right? These are permanent staff scientists like you would find at Canadian Light Source or Brookhaven National Lab. And then cross-cutting to these, we have both an AI and automation lab where we have people with expertise in robotics, AI, and reinforcement learning there to support and develop tools that can be used by each of these self-driving labs. And then also unique maybe to Canada, not so much our friends to the south anymore, social sciences. So on the one hand, you want to make materials, you want to make self-driving labs, you have to make a business case for them. You have to understand what your value proposition is so that people can get excited about it and understand why they should do this. On the other hand, we have to consider sustainability and impact on communities as we develop new materials. PFAS and forever chemicals is a wonderful, terrible example of a company moving fast, developing a new thing, and viciously poisoning the community around them and potentially the world. So we have to consider those up front through conversations. All right, so what does $500 million buy you? It buys you a whole lot of really cool hardware. Whoop. Apologies. I wanted to get doesn't matter. So you saw the robots moving. Each one of these tools represents a different self-driving lab. And, I'm a builder. Sometimes you invest $1 million in a ChemSpeed automation platform. And then sometimes you build your own tools. And sometimes you work with your collaborators at national labs to build something that goes from kind of a little bit janky from a graduate student, postdoc, good stuff, to basically a professional grade automated platform for performing sequential experiments. That's cool. We can build these, we can develop these. And within my own group, again, my focus is on high throughput materials discovery. We've been building autonomous research agents now for about 10 years. And I have a very strong emphasis within my group on trust in AI. Being able to trust the predictions and in some senses, the AI being able to trust our labels. We'll talk about that. And we're constantly, you build a platform, you go through all the rigmarole, it's a years long process. Once that's done, it's not good to just be like, and now it's my robot, now it's my AI, now it's my data. And so my group has a very strong emphasis on open science platforms, getting the plans out there, getting the data out there, and getting the code out there. Okay, so talk is about bias in AI, and all I've talked about are robots so far. So let's jump in. Bias in AI comes in many flavors. I preface this slide by saying, first and foremost, I'm a natural born American. I can talk about our problems. Bias in AI comes in a lot of different flavors, right? This is the famous Boston housing market data set. The first bias comes in how we decide to describe our inputs. And so in the case of the Boston market housing data set, there's this term B, which is a parabolic distribution of the proportion of African American students in a particular town as a relation to find a relationship between that and a house price, right? So this is the bias of how we describe a system. This is an image from accuracy of facial recognition technologies that shows systematically all of the bigs are systematically worse at identifying darker female human beings. This isn't because the algorithms themselves are prejudiced. This is a bias of how we select and where we select to look. This is an example from Detroit of, hey, let's get a bunch of cops going around and let's make sure that they're in the right spots. This is a plot of predominant ethnic distribution in Detroit. Pretty strong correlation going on there. And that comes down to how we decide to label outcomes. And then finally, there's the old Hindu allegory about blind men trying to disguise what's the nature of an elephant. And that's how we look, right? That's how we decide to look at a particular system. And there's other biases that we could talk about. Let's talk about material science because that's what I do. I can actually speak to that. So we understand as scientists that there are different flavors of ground truth, right? There's the true ground truth. This is an object. I can hold it in my hand. And because we believe in causality, there exists a set of rules that determine what state is this matter, What are its interactions with the world around it? But those are too complicated. We have to estimate. And so we as scientists live in this world of tilde, ground truth, right? We have it interact with an electron, we get a diffraction pattern, and we have this tilde state that uses simplified rules for interactions, simplifications, idealizations of the state, and rules that we've decided are universal for arrangement. For an AI, though, the label of what this ground truth comes down to who labeled the picture, right? These are two Nobel Prize winning individuals. One of them won two, one of them only won one. If you ask Linus Pauling what this is, it's an example of bad science, get back in the lab and redo it again. If you ask Danny Shechtman what this is, he says it's a new state of matter. It's a quasi-crystal. We've never seen this before. And so the AI on the other side of this creates these predictions, assuming that our labels are infallible, that they represent true ground truth. And another thing we'll get into is that any new prediction, the data underlying those fall under the same distribution. And so again, we have an unknowable ground truth. We have an approximation that says this is a crystalline material. And then based off of the user bias heuristics, we could get very different labels. Okay, so let's talk about measurement science. Let's talk about user bias and interpreting data. And so this is Runza Zhang, he actually now is a fourth-year graduate student. I got to update that. When we look at spectroscopic data, there is an awful lot of bias that goes into interpreting it, right? When is a peak truly a peak? When is it noise? What is the true underlying physical model? And so this is biased based off of who you are, what papers you read, who is your PhD advisor, what's your community, what's your view of the physical system, and how bad do you want to get a Nature paper? And so we're going to take electrochemical impedance spectroscopy analysis as an example, and we're going to walk through a method of first identifying where user bias comes in and proposing a couple of statistically sound methods for potentially debiasing the analysis. So the common thing is we all know the Little Prince. This is a fedora. No, it's not. It's a snake with an elephant inside of it. Who looks at it, an adult versus a child, determines what's the true physical nature. Okay, so I'm realizing I'm sitting in front of a bunch of mathematicians, computer scientists. I'm going to take a little bit of time to walk through this slide. So this is an EIS, or electrochemical impedance spectroscopy data set. These blue dots represent the physical measurement, and these represent mass transport, so the movement of electrons and ions in an electrochemical system, which are defined by, first and second order mass transport differential ODEs and PDEs. As a material scientist, that's too hard for me to solve en masse. And so we use a construction that's called an equivalent circuit model. So basically, we treat our electrochemical system as a series of resistors, capacitors, inductors, constant phase elements in series and in parallel. And we use that to map the frequency response of our system, of the resistance of our system. What you can see is that, sometimes systems can be relatively simple, but the user who's performing the analysis decides they need a circuit that contains two of these things that are called Randall elements. What we wanted to do is we wanted to develop a tool that allowed us to debias this. And so we created this tool called AutoEIS, which combines an evolutionary algorithm called gene expression programming, which basically creates a zoo of potential equivalent circuit models that could potentially fit this data. And then on each of those circuits, we use something simple. We just use good old-fashioned Bayesian inference to infer the values for each one of the components in every one of these circuits. We can then use a heuristic. It's always a heuristic, but it's encoded bias now, that we prefer that our circuit components be normal in shape. We can explicitly quantify this, and then we can compare the results of our particular system against a human-created system. And we can make a statement that our circuit is a little bit simpler, contains one less random element. All of our posterior distributions are normal. The posterior prediction well describes the data, as opposed to the human version, which was more complicated. It involves now a couple of circuit components that are very strongly non-normal in nature. And so you can present to the user, look, here are the circuits that we think are best fit. You decide what you want to use. What's cool about this is then you can ask the second question. People have been using, for instance, this circuit to fit a particular phenomenon forever. Under what set of conditions, under what set of values is this actually a relevant fit for your system? And when are you overimposing your human bias on top of it? And can we tell you the difference? And so what we did is we selected this system. We did a series of simulated EIS, which is easy, straightforward. And then we were able to identify very clear boundaries between when this system seemed to be statistically plausible, when you were justified in using it to fit your data, and when you were not. And in the place where you're not, that's an opportunity then to reconsider your data, reconsider your biases, and step back and consider maybe I should use a simpler system because there's just not enough signal to support the complex model that I proposed. The next side of that is another form of bias from users, and that's that they want, it's FOMO, it's fear of missing out. We want to measure every single frequency. So EIS measures from hundreds of kilohertz, which is wicked quick. And some people, if they're trying to look at really slow phenomena like diffusion through a solid interface, will measure down into the millihertz range or even sub-millihertz. And so you can imagine that a single EIS measurement could take 20 minutes to an hour to perform. The question that one could have, though, is, did I need to measure at such low frequency to be able to get statistically plausible understanding of what would have happened at those frequencies, given my encoded bias of my model for the physical system? And the answer is, otherwise I'm not talking, right? The answer is, depending upon the system, depending on the magnitude of the values, you don't need to measure all the way down to low frequency. If you are justified in your bias for what circuit fits your particular data, we understand that, you know, it's a cocktail party problem. You have multiple people talking, one person's shouting at one point, one person's whispering, and maybe they flippity flop. And the question is, when can I just start to hear that second person talking sufficiently so that I can work out who it is? And we found, in fact, that we can drop a third of the EIS, take the measurement time from like 30 to 40 minutes down to less than a minute, and still be able to get good statistically sound inferences on the components, basically be able to see where we didn't measure. Okay, I want to be a little bit cognizant of time, especially to make sure that we have time for questions. So I'm going to skip these slides. Measuring measuring error is non-trivial. It's like measuring distances, right? When we're in school, we're taught L1 Manhattan block distance, we're taught L2 distance. You know, maybe we teach cosine similarity, and in our minds that solves the distance problem. It doesn't. measuring distances, and in particular, trying to measure distances when you already have a reasonably accurate model or you have a very high dimensional vector is a non-trivial process. And so, but that's problematic for us because we want to train models on these things and we want accurate fits to know that we have a good understanding of the tilde ground truth. And so one has to consider very carefully how to measure distance, when is it accurate, when is it inaccurate, and also there's another side of it, which is computational efficiency, especially when you're starting to do things at scale. I'm going to skip these slides, but it's really interesting stuff. This is the fun stuff. All right, so my group, right? We train machine learning models all the time. I teach a class on how to teach machine learning models. The problem is we understand that models and new predictions have to follow IID. They have to be identical. They have to be independent and identically distributed. ID is hard. A priori knowledge of what is identically distributed for new samples is challenging. And so a question that we have, right, is what do we mean when we say something's out of distribution? Is it quantifiable? Is it even legitimate? Does OOD necessarily imply extrapolation or something is difficult? And are we misrepresenting the generalization of our models by not carefully considering when a prediction could potentially be truly out of distribution? Okay, so we're going to do a cool thing, right? Because there's data, there's material science data. So there are three major DFT data sets that are public and open: OQMD from Northwestern, Materials Project from LBNL, and Jarvis from NIST. We're going to look at all three of them. We're going to look at structurally and chemically what we would consider to be out of distribution tasks, and we're going to see how well our representation of what's out of distribution and how well our material science bias holds. We're going to look at three properties: formation energy, band gap, and elastic modulus. And just to show ourselves that we're not losing, just to show ourselves that our results are relatively WOLOG, right, without loss of generality, we're going to consider tree-based models. We're going to consider state-of-the-art graph neural networks and large language models. And we're just going to systematically evaluate them across a series of tasks to find out when they break and when they are unexpectedly good. So first one, this is for enthalpy of formation. This is a line. This is an atomistic line graph neural net from our friends at Kamal Chowdhury and Brian DeCoste at NIST. This is the periodic table if you've forgotten your chemistry. Yellow here means that I held out, for instance, sodium, and every compound containing sodium was held out of the training set. I trained on everything else, and then I tested on sodium. Yellow means the prediction was surprisingly good. So for instance, I can not consider iron at all, and I can get an R squared of 0.989, which is comparable to what I would have gotten if I had considered iron. I can hold out something wild like cadmium or bromine or chlorine and systematically be able to predict the enthalpy of formation really well. There are several notable exceptions to this rule: oxygen, fluorine, and hydrogen. Each and every one of them, if I hold them out, I get an R squared that is either negative or zero. And so I can say, generally speaking, for enthalpy of formation, for a graph neural network trained on, this is the Materials Project dataset, I'm good across the periodic table except for hydrogen, oxygen, and fluorine. Those are god-awful. Likewise, I can leave an entire column of the periodic table out and still be able to predict enthalpy of formation reasonably well. I can do the same for, I did wrong direction, it's fine. I can also remove rows from the periodic table and be able to predict that row of elements reasonably well. This is not data source or modeling architecture dependent. So I can take the enthalpy of formation. I can look at an XGBoost model on materials project, and I get roughly the same performance. I can look at XGBoost on the Jarvis dataset. These are all different people doing different flavors of DFT with different background corrections or not to their final enthalpy values. And I can do this on OQMD, and I get the same problem every time. Firstly, well, problem and opportunity. Opportunity. I don't need to know iron compounds in my data set. I can predict those no problem. Problem, if I don't have oxygen in my data set and I try to predict oxides, I'm pwned. Fluorides as well. And that's even a little bit weird because, you can say oxygen's a special animal, and it is. It's a special animal in the periodic table. But fluorine, right, it's a halogen. I should be able to get very similar information from fluorine that I would have gotten from chlorine, or from bromine, or from iodine, right? They're also halogens. They tend to form the same type of bonds. They tend to be just as their electron has just as high electron affinity or close as chlorine, but it doesn't work. Okay, I do want to first and foremost point out, right, that enthalpy isn't the whole story. If we try to do this same study on something like band gap or modulus, the whole thing falls apart like a house of cards. So what that says to me, and this is my opinion, this is like my opinion, man, right? It's not necessarily a DFT problem, right? It certainly isn't a model capacity problem. I don't think it's a data problem. It's a representation problem, whereby there is something special about the electron interactions that are disregarded in our current modeling descriptor set that is just a little bit too important for the states of oxygen, hydrogen, fluorine. That's just not captured. Likewise, on the other side, band gap and modulus are tensor properties more so than their scalar properties, right? There can be direct and indirect band gaps. Band gaps come from band structure. Modulus comes from derivatives of potential curves. They're a little bit trickier to scalarize. And the representation, again, for band gap or for modulus is very strongly related to electron interactions rather than just position of atoms and identities. Okay, so again, not model dependent. Doesn't matter if it's a line, GMP, XGBoost, random forest. Across the board, we can leave an element out and the models perform functionally equivalently. You'll notice that they do hit a different threshold, right? Their accuracy threshold is slightly different. That's just the nature of the models, right? XGBoost is just not as good as a graph neural net. I will point out we worked with our friend Aji Dieng from Princeton University on their LLM prop, which takes a text description of the crystal structure, takes a fine-tuned transformer model, and uses it to predict quantities like enthalpy, band gap, and modulus. So by and large, these models perform more or less equivalently to one another in distribution. LLM prop, if you remove an element, it's a disaster. It's just an absolute disaster. It has learned some sort of spurious relationship between the text description of a crystal structure and outcoming property that does not generalize well, just as a caveat. Okay, so let's talk about, I have maybe 10 minutes. Let's talk about how where we looked influences where we can search. Because if I'm talking enthalpy right now, you're thinking in the back of your mind, it is almost a solved problem, right? Except for three very special cases, oxygen, fluorine, and hydrogen. I have good, robust, generalizable models to predict the enthalpy of formation, right? If a compound is going to be stable or not, for almost the entire periodic table. Good to go. So that's not the case, and it sucks. So again, this is a line from our friends at NIST. This is the benchmark from MatBench, and this is old. Align has since been supplanted as the #1 best performing model, but it's still in the top 3 or 4. So this is its mean absolute error as on the MatBench formation energy benchmark. It is a fantastic model. So let's do a stupid thing. Let's take that model, which is trained on Materials Project 18, and I like alloys. Let's use it to predict the enthalpy of formation for MP21 alloys. And let's see how the model does. Orange is the data that's in the training set, and blue is the data outside of the training set. This is the parity plot, right? So DFT versus Align. The errors are huge, right? They are nowhere near one another. And there's no trend, right? It's not like a systematic underperforming or a systematic overperforming. It is random. And when I say overperforming, this 0 point for us is really important. A negative enthalpy of formation means it's likely to be formable. A positive enthalpy of formation means that you're going to have to work really hard and you probably can't make it. The state-of-the-art model in an exploratory world is as bad as a random guess. This is the whole point, though. We don't train the models to one-up our friends on the benchmarks of the data that's already there. We train our models to look where we haven't been yet, and they perform poorly. This isn't so, an easy thing. When my postdoc showed this to me, he's like, oh, look at this. I'm like, it's a graph neural network. That's the problem. It's overfit. Let's use something a little bit high capacity, but maybe it's got a little wiggle to it, a little bit less wiggle. Let's do XGBoost. Let's do random forest. Let's do linear forest. They're all the same, completely different representations. Feature-based versus a graph, atomistic line graph of a crystal structure. Completely different basis, way of representing materials from one another. Same outcome. Absolutely same outcome. That's a bummer. I don't want to leave you, it gets worse. It gets worse. So there's this idea, right, that, well, that's fine. It's big data all day, every day, right? Big data is going to save us. And so if we just continue adding more data to the mix, these out of distribution predictions, these poorly performing predictions are just going to magically get better. Well, we can simulate that, right? We can look at in distribution predictions for something like iron or quinary, and we can look back at our elemental stuff, right? And we can look at fluorine, hydrogen, or even something that wasn't as bad, but still not great, lithium. And as we increase our training data set size, we don't follow neural network scaling laws, right? Unless we're doing a random search, in which case we might luck out and grab a hydrogen or a fluorine containing compound or two and suddenly shift the distribution. Neural net scaling laws do not work if your materials are representationally out of distribution. You don't win just by adding more data. But you can win, I think. You can win. And so let's go back quickly. Notice this garbage, right? We got garbage over here where the model is just predicting absolutely terribly compared to the parity plot. But because each of the models are based off of different architectures, have learned different representations of materials, we can turn garbage into gold, right? We can take the models, look at where they disagree the most, and this isn't mathematically compact, this is not mathematically correct, but it's a starting point. Let's look at the compounds that maximize the difference in model predictions. And let's add those into the training data. And let's see how quickly we can recover the original performance of the model. So this is the MP18 to MP21 data set. This is a UMAP projection. So it's a reduced dimensionality projection of this is the composition and Mat minor and pi mat gen representational features of the material. This is our in distribution data. And these are in particular some of the compounds we were doing a really bad job of predicting. Ordinarily, one method of filling this in would be just to use the UMAP and then plus random. And over here, you can see our active learning curves. It does a reasonably good job, but it is also off optimal. If conversely, we just ask how much do the models disagree with one another and choose the ones that maximize our disagreement, we get a much more rapid convergence to a model that is just about as well performing as it could have been if we'd selected an optimal split. And so, yes, where we looked influences what we can predict, but as long as we can identify simple methods for figuring out where we haven't looked before, the models can be self-corrected with new observations relatively quickly. Vitaly, I think I have 9 minutes left and we have to have discussion as well.
Sure, as you like. Yeah, you have 5-10 more minutes, so including a discussion.
I want to do one more case study, and I'm sorry. If it goes
Yeah,
too long, I
awesome.
really
No,
apologize.
no problem.
So let's talk about the bias of expertise. The bias of I'm the person who does the thing I know better than you. So a couple of years ago, I was working with a company out of UBC, and their jam, their thing, is pumping salty water out of the ground, doing some fancy crystallization stuff, and turning it into battery-grade lithium carbon. And so their technology, the way that it works is they do selective crystallization through temperature swing. So they have two reactors that they're flowing the salt water through, a cold reactor and a hot reactor. And it's in the hot reactor that they're able to separate out the battery grade lithium carbonate. And then in the cold reactor, they're doing a little bit of makeup chemistry, and they cycle this for a period of time. And they've demonstrated this. This has been in business in Arkansas for a number of years next to a bromine mine. So it works. But then the question was, if we wanted to do this somewhere else, what are the range of brines, of salty water, nasty, dirty water that our technology can accept? And what are the range of processing parameters that we can tweak our model to in order to still come out on the other side with battery grade lithium carbonate? Right. And we're talking like 50 ppm of like magnesium. It is super clean. Great project. You know, I'm a AI guy and I do experiments. So I'm like, yeah, with process control parameters, we're going to do a Gaussian process regression model, right? We're going to use we're going to use different acquisition policies, and we're going to find these new things, and we're going to select optimal conditions, and we're going to get our predictive uncertainties, and we're going to roll, bang. Couple of problems popped up. One, this is real chemistry. And so I was getting maximum 2, maybe 3 experimental data points per week. So over a course of a 1.5-year project, we ended up with 150 total experiments, 50 of which had already been done. Second problem, they knew their condition that worked for their material and that worked for that brine. And when you ask them what happens if I change this or that, is it smooth? Is it rough? Where are the boundaries? They don't know, right? They're running a chemical plant. This works. We spent 6 months trying to develop models to predict battery grade lithium carbonate, and we could not find anything. We were chasing experimental uncertainties, we were chasing variability, we were building different models, different interpretation tools. We got nothing for 6 months. And so in our weekly meeting, we're about to sit down, and I'm at the point where it's like, it's not you, it's not me, right? It's us together. You need to go and figure out your side of the story. If there's anything wrong with your experiments, we're going to sit down and we're going to have a hard think about our models and our modeling architecture and what on earth is going on, because this isn't working. And Shayan, who was a graduate student at the time, walked up to me and he said, look, you know, they've been asking us to keep this cold reactor super cold, right around room temperature or lower. Lower is better. They want this hot reactor, as hot as it can get, right? And they want a sort of difference in temperature of at least this. I've been modeling this now for 6 months, and everything in the feature importance analysis is telling us we got to heat up the cold reactor. We got to take that cold reactor from 20 degrees or 15 or 10 degrees C, and we got to pump that baby up to 60 C. And this is our Pareto frontier. This is where our predictions are, where we're going to minimize the amount of magnesium and calcium in our thing. And this is telling us about how much we have to change the temperature. You know, SHAP analysis is telling me that T cold, when it's hotter, it's better. And I'm getting good error bars on that, so I feel reasonably confident in that outcome. We need to do this. And now I got to convince the chemists to change their condition. I got to convince them to go hot. And no, it violates thermodynamics. The thermodynamic principle by which this works dictates that we have to have cold as possible and as large a temperature difference as possible. Well, relationship's over, right? We're about to walk away from one another. So let's do it. Let's do 1 week. Let's do it our way. I bet you a donut. I bet you 1 donut that this will work. So against their will, they went ahead and did the experiments. And that week, we got battery grade lithium carbonate. And for the next year, we got nothing but battery grade lithium carbonate. Super cool story. On the other side of that story, the next morning at 8 o'clock in the morning, when I arrived at my office, I found a bag of donuts hanging off of the doorknob that had been flown overnight from Vancouver to Toronto. Okay, so I want to be respectful of everyone's time. Out of distribution is not what we think it is, right? And when we're thinking about training these models and saying they're generalizable because we've got the biggest data set and the best feature set and the most expressive model imaginable, time and time again, you're going to find that these prediction tasks are unreliable, right? We need to consider as a community, in my own community, but more broadly, once a benchmark is such that people are starting to hit that second decimal point in terms of improvement, you need to come up with a new benchmark. We need to constantly be pushing on our models and finding the places that they break. My own feeling for my own field is that explicit electronic featurization is probably pretty necessary for our next step, both in describing what's happening with oxygen and fluorine, but also in predicting band gap and modulus. Measuring errors is not trivial. So this is my village. I'm the idiot. Thank you so much for your time.
Thank you, Jason. So please thank Jason for the insightful presentation, physically or virtually. Right, let me now stop the recording so that we